parallel computing. So I want to make a quick note here that the underlying theme here is parallel computing, although I'm going to be talking a lot about GPUs because that's what I know about. And actually, it has a very beautiful history when you talk about GPUs. Okay. And so we will look at a couple of other systems very briefly. I'll just mention. And then we will look at a couple of other systems and the underlying, oh, sorry. So the underlying goal is anyway parallel computing. So you don't need to get distracted because of GPUs. You can just think of parallel computing, except for these couple of slides where I'm going to be talking about GPUs more often because that's what I know about, right? So let's start looking at GPUs, games, and movies. Until a few years ago, consumer-grade GPUs were only bought by enthusiastic gamers, right? And higher-end GPUs, which are more expensive, were bought by movie studios and agencies involved in supercomputing, like national labs and those design industries, like if you are involved in aircraft design or automobile design, they were using lots of parallel computing, and even oil and natural gas exploration, they were using a lot of supercomputing or parallel computing. And but in popular opinion, if you had a GPU 10 years ago, it's very likely that you were a gamer. So what is it about games and movies that made GPUs very useful? We all know it is parallel computing, but what kind, right? So if you think about games or movies, it is all about object positions. You have a bunch of characters in the games or in the movies, and they keep moving around. They move fast, they burn, there are smoke, cars flying around, and so on, right? So suppose we have this 2D monkey and we have the location of the monkey, XY coordinates, and we are building a 2D game and you want to move this monkey to a different position on the screen. What you do is you decide how much to move in the X direction and how much to move in the Y direction. And if it's 3D, you will have one more dimension to add and so on, right? Here in this case, I will move TX in the X direction and TY in the Y direction to reach the new location, correct? Which is nothing but matrix transformation. You take the initial coordinates and multiply it with this new transformation matrix, and what you get is the new coordinate. And we all know that matrix operations are extremely parallel, right? So you can do several computations in parallel because some of the row column operations are independent of another row, another column operations. So there is a lot of parallelism in matrix operations. So it's not just the story toy, it's not just movement of objects, but there are several other things which are just matrix transformation, like rotation. If you want to rotate a monkey, if you want to hang down from a tree, deformation, if you want to smash the monkey, right? Or any object that is deforming because of stress or reflection, and many more are just matrix transformations, and they are extremely parallel. So this made GPUs really, really good for gaming, right? Because GPUs are nothing but lots and lots, thousands of very small compute cores. If you take an Intel CPU, they also have multiple cores, but they are like 10 or 12. But GPUs, an average GPU will have like 2000 or 3000 cores, right? But they are not as capable as a CPU core. But for these matrix of operations, they are very good, right? So they cannot do much, but whatever they can do, there are lots of tools for you to exploit, right? So what about high performance computing, which is like supercomputing, right? Let's look at some high performance HPC applications and see why GPUs became useful there. So how many people recollect this equation? We have all studied this during our undergrad engineering days. At least for me, I came to realize the scale of the importance of this equation only much later in life, and I feel very ashamed about it. And this is the famous Navier-Stokes equation. It describes the flow of incompressible fluids, and it is very widely used in games to simulate smoke or fire and so on. Whenever you see smoke or fire in movies or games, they are underneath, they are using a variant of this equation to simulate that. So you can just go to YouTube and look at Navier-Stokes equation simulations. Then it's very surprising how difficult it is to simulate and what kind of computation goes inside. And it's very widely used in weather modeling, to model ocean currents, to model turbulence. And if you're involved in automobile design, to model the flow of air around a car or flow of wind around an aircraft wings, these are all modeled using this Navier-Stokes equation or some variant of this Navier-Stokes equation. So that's why GPUs, because these any incompressible fluid, you think of it as different layers, and each layer you model it, and it's a very highly parallel computation. And it's no surprise that all the supercomputers that are involved in such operations like fluid dynamics or design and so on, they use lots of GPUs. So the most expensive supercomputers of all, they are also nothing but the massively parallel computation engines. Like they can be used in geology, right? And they are used in weather forecasts, and they are used in aircraft propulsion design to see how well the blades of an engine can cut through the air. And that requires a lot of computational fluid dynamics, basically the Navier-Stokes equation. And more recently, they have also been used to find cure for this COVID-19 that we are going through, right? So we saw games, we saw movies, which are again matrix transformations of objects, and we also saw this high performance computing applications. They all involve parallel computations, right? And since GPUs have thousands of cores, compute cores, they turned out to be great for such applications. But what about AI and specifically DL? And this is from a blog post I came across recently, and I just decided to use it right away because this is the best description of ML I could find that fits in one slide, right? You have all these features, X1, X2, and you have the weights, you have the weight matrix that you're trying to train and learn. And you see that this tiny network in just one pass involves two sets of matrix multiplications, right? For the first layer and for the second layer, right? So you can contrast this. So you can see the amount of parallelism in this toy example. The ResNet 50, right, one of the benchmarks for image classification, it has 50 layers and about 23 million trainable parameters, I guess. It's of the order of 23 million, right? So you can imagine the scale of parallelism available in such networks, right? So that's why if you have GPUs, the more cores you add to it, you get, magnitude of efficiency more than using CPUs or any other system that is not able to exploit this parallelism. So you know already by looking at this picture, or if I throw in several cores, these matrix operations will get parallelized, and the more cores I have, the better I can compute, correct? But why only now? It's not that GPUs were invented only in the last 5 or 10 years. GPUs are not something new. We had GPUs for decades. Maybe those GPUs 20 years ago were not as powerful as the ones that we have today, but we still had them, right? And they've been around for around 20 years at least. And the idea of using GPUs for machine learning, that's also not new. If you read this research paper using GPUs for machine learning, this is from 2005, right? 15 years ago. And it already shows some moderate speed up, but not many people, Facebook, Google, they were not using this 15 years ago, right? And we all know HPC, gaming, visual effects, all these have been around for decades. We all have seen Jurassic Park and all those things. So how did AI and GPU get into the limelight only now? So there are three big factors that led to this GPUs coming to the limelight. I shouldn't even say GPUs. In general, parallel computing and for machine learning, bringing that to the limelight, there are three big factors. The first of all is big data, because almost everyone has a smartphone, right? And the sensors have become really, really inexpensive. Your camera is a sensor. It is an image sensor, right? And all smartphones have at least one image sensor, at least one camera. And usually we make it a point to photograph our food. even if we don't end up eating it eventually, right? And there was this proliferation of internet, mobile internet in particular, that made sure that we can share the images that we take with everyone, and everyone can share it and send it around and so on. And it's not just images, as you can see in this snapshot, we are generating lots and lots of data every minute of the day. It's not just images, but there are several kinds of data. So someone is gathering all this data, and they need more and more parallel computers to digest this data, to make sense of this data, right? So having data, just having lots and lots of data is not enough. So this is, although the biggest factor, it generated lots of data. So now you need to build bigger computers to sit and analyze this big data, right? And again, the second factor is computing power, and mostly helped by Moore's law and other technology innovations, right? So this news article, right? Even the headline sends the right sends the message. Actually, your smartphone is millions of times more powerful than Apollo 11's guidance computers, right? So we may decide to use our pocket computers only to poke our friends in Facebook, but it is still a very, very capable computer. And another factor is distributed computing. You can think of Gmail, you can think of other Google services like Google Maps, or you can think of AWS and so on, right? So if you cannot do it in one desktop computer, you just distribute the computation and gather and accumulate the results. And we were able to get away by distributing the computation, we were able to handle lots of data. The other one is growth of data centers. I'm saying this is one of the big factors because today you don't need to own and maintain an expensive compute infrastructure anymore. We can just rent it out as needed and give it back when our computation is done, right? So the first big factor is big data. The second big factor is computing power. And the third factor is software platform. It's not enough if you have lots of data and really massive computing engine, but you should be able to exploit that computing architecture, right? You should be able to program that architecture so that you can get what you want out of it. So something like CUDA that allowed us to program and distribute our computations into the many thousands of GPU cores. And we have libraries today that accelerate even the DNN operations like softmax, ReLU, and all those things. They're called QDNN, like CUDA deep neural network libraries, right? So these three factors, primarily the first two, big data and computing power, they are relatively new. We did not have awesome phones 15 years ago, although we had this computing power. We had GPUs around 20 years ago, as we saw, but we didn't have lots of data because we didn't have lots of smartphones and cameras. They were still expensive, so we were not generating lots of data, right? And even computing power, it wasn't really affordable, correct? So you had to buy even relatively efficient or powerful desktop was pretty expensive those days. But they were used for high performance computing because supercomputers, the national labs could afford it, and they had to afford it in order to model weather and so on.